Yes. So in the previous class, we stopped at a stage where you asked the question. One of you asked the question regarding the coupling with the nitrogen nucleus. Is it not? In fact, since that was almost at the end of the class, we could not address this question at length. So the first part of my lecture today will be on how the ESR electron signal undergoes splitting due to coupling with nitrogen nucleus. In fact, you know, which are the stable isotopes of nitrogen? N14 and N15. In NMR, and of course, N14 and N15, and what are their I values? For N14, I is equal to 1, and for N15, I is equal to half. But looking at the I values, you can tell that they are, of course, magnetically active nuclei. So N14 and N15 are. But do you ever observe any type of interaction and a result of interaction in the spectra, NMR spectra, due to probably the proton coupling with nitrogen or something like that? Do you ever see nitrogen reflected in the spectrum of NMR, either C13 or HNMR? Do you see anything, any sort of interactions with nitrogen nucleus? Hello. Yeah. Question. Answer. Answer. Hello. Oh my God. Why? There is absolute silence from your side. Have I muted? No. Yes. So, Chandana Priya, you're online. Hello. I mean, anybody can answer this. Is there any sort of interaction with the nitrogen nucleus in NMR? Hmm? No response. Why? Ah, yes. Tell me now. Yes. Is there a technical issue or subject issue? Why you're not answering? Babus are there? Babu E and Babu V? Hmm?
Sir.
Yeah. What's your opinion, Babu? Do you see any type of interaction with the nitrogen nucleus in the NMR spectroscopy? Hello.
Yes, sir.
What type of interaction? Do you see a splitting of the hydrogen signals due to coupling with nitrogen nucleus?
No, sir.
No, fine. But doesn't it appear a bit strange? Because nitrogen is not a magnetically inactive nucleus with I is equal to 0. Nitrogen has I value, non-zero I
So
value.
is equal to, yes,
Yes, I is equal to 1 for
1.
nitrogen 14. Is it not?
Yes, sir.
Then why do you think there is no interaction? There should have been, right? All nuclei with I
Yes, sir.
non-zero value should have spin interactions, either with electron or other nuclei around. Why do you think then? Nitrogen is silent in the NMR. Yeah, I think this is a better question. Why is nitrogen silent in the NMR?
Abundance kadme irodunದು.
Yeah, okay. So let us point abundance. You know, nitrogen is one element wherein it is almost monoisotopic in the sense nitrogen 14 has a natural abundance to an extent of 99.4%, and only 0.6% is nitrogen 15. So there is no shortage of abundance, because 99.4% of the nucleus has I is equal to 1 value. But at least the answer based on abundance we can give for why nitrogen 15 is silent. Is it not? It is not making any interactions because of its very low natural occurrence, only 0.4% compared to rest of the nitrogen nuclei. So nitrogen 15 interaction either with a nucleus or an electron nearby is ruled out. Why? Although its I is equal to half, because of its very low natural abundance, almost negligible, it doesn't interact with the nuclei, so or with the electron. Therefore, there is no question of discussing hyperfine splitting due to nitrogen 15. But nitrogen 14 presents a curious case. I is equal to non-zero, I is equal to 1, but it is still silent in the NMR, but it's not making any interaction with the nuclei. Why? Have you reasoned it out? Anybody? Have you ever thought in this direction? Why nitrogen is so silent in the NMR? In fact, there are modern NMR techniques which give you nitrogen 14 spectra also. By doing a lot of modulations and manipulations in the instrumentation part, and in the way the signals are generated, nitrogen 14 is made active in the NMR also. So that means what? I is equal to 1, nitrogen can still be a nucleus of some activity. But why we are not observing any interaction with I is equal to 1 nitrogen 14 is, see, okay, when I start the topic of NQR spectroscopy, that is nuclear quadrupole spectroscopy, I will explain more on this aspect. But as of now, you please understand that all those nuclei with I is equal to greater than half, so like I is equal to 1 is of course greater than half, they have something called nuclear quadrupole moment. And this nuclear quadrupole moment makes the, because of this nuclear quadrupole moment and rapid spinning of the nuclei, a combination of these two doesn't allow that nucleus to have a spin interaction with the other nucleus, neighboring nucleus around. So all NQR active nuclei remain to be silent in NMR always. They tend to be silent in NMR, NQR active nuclei. So this is not regarding, the inactivity is not because of I is equal to 0. It is because though I is non-zero, they are NQR active. They have NQR nuclear quadrupole moment. Because of this factor, they do not show up in the NMR. Anyways, what is NQR? All these things we will in detail we'll see when we take up NQR spectroscopy. As of now, you just understand this. Now, but what should happen to this radical? Now, I've shown you a radical in the picture, right? You have a benzoyl group attached to CHNO, and there is a radical. Of course, the dot should have been on nitrogen. Anyways, no problem. Assume that the nitrogen dot is on the nitrogen, because I could not draw a structure like that. I've just shown you like this. Fine. How many signals do you expect? How many signals do you expect for this radical? If the nitrogen has the free radical electron on it, odd electron on it, how many signals do you expect? Hello? And like nitrogen 14 in the NMR, you people have also gone silent. Why? Some issue. Why? Yeah, Sangeeta. Present, right? Yes, Sangeeta. Fine. Okay. So how many signals do you expect, Sangeeta? Now let us consider, because of NQR, nitrogen is not making interaction with the electron. Let us, for the argument's sake, consider that nitrogen is inactive now. So how many signals do you expect? Sangeeta?
4. 4.
Louder.
4, sir.
4. Why? How? explain the splitting pattern? Why do you expect 4? Which nucleus is it coupling with? Yeah. Yes, now. Fine. Yes, Sangeeta, go ahead. Now the free radical is on nitrogen. Which is the other nucleus which I non-zero value in this whole structure?
Hydrogen.
Ah, very good. Yeah, fine. So if it couples with hydrogen, how many signals do you expect? If the spin interaction takes place with hydrogen, how many signals do you expect?
2 signals.
How many? 2. Good. 2 signals because n+1 rule. So 2 signals you expect. That's what. Okay. Now let us see the actual spectrum of this radical. This is the spectrum. How many lines are you finding in the spectrum? How many lines? Sangeeta.
Yes, sir.
Yeah, you are still on a hot seat. So the questions are to you. How many lines you are finding here?
6.
Ah, yes. So there is a contradiction, right? We expect only 2 lines because the coupling should take place with hydrogen. How are we getting 6 lines then? What can be the reason for obtaining 6 lines? I mean, you can make a guess here because I have not discussed this topic yet. So you take a guess and answer. What could be the reason here?
Interacting with other nucleus.
Very, very good. It can,
Benzene hydrogens.
yes, it can be due to interaction with other nucleus. But which are those other nucleus? Of course, carbon, oxygen, these nuclei cannot be magnetically active because by default, they have I is equal to 0 value. However, there is one more nucleus, nitrogen, with I is equal to 1 value. So since we have got 6 lines, and if an electron couples with a nucleus with I is equal to 1, how many lines do you expect? In this, what is the splitting? If it couples with I is equal to 1?
1.
3.
Good, because the formula to calculate the number of lines is 2ni.
2ni plus.
Yes, yes. Okay. So I is equal to 1. So 2 into 1 into 1 plus 1. You should get 3. Actually, that's happening. In fact, we are right. If we use nitrogen coupling also and account for the spectrum, we get 6 lines. Now, then this brings to our question that, I mean, this is what is the conclusion? But that nitrogen is no longer inactive and silent in the ESR. It is only silent in the NMR, not in the ESR. So whenever you have a radical on nitrogen, I mean, in the sense the electron on nitrogen, in a radical, you have an electron on nitrogen, or because of delocalization, the electron can interact with nitrogen. Please calculate splitting, including nitrogen also. Fine. So if there is a single nitrogen, 3 lines. If there are 2 nitrogens interaction, 2 into 1 into 1 plus 1. So 2 to the 4, 5 lines. So go on doing like that. What is the take home lesson? What is the summary of all the discussion we have made? Don't omit nitrogen from calculating your hyperfine splitting patterns, or from calculating the total number of lines obtained from hyperfine splitting. Don't omit, don't skip nitrogen, use it. Fine, that's okay. But we have not still answered this question. Same question I will ask again. Why a nitrogen 14, which is inactive and silent in NMR, becomes active and magnetically active and interactions are seen in ESR? That is because of this important phenomena called time scale of resonance. I think this concept you would not have learnt with a stress. I mean, you would not have learnt in detail before. But of course, it is not very much directly related to the techniques of the spectroscopy we discuss usually in our chemistry. But there is one phenomena called time scale of resonance. Okay. Now, in NMR, what is the frequency of the radiation we use? Which range of radiations we use for the resonance in NMR?
60 megahertz.
Radio waves.
60.
Yes, radio waves basically, is it not? So the frequency of the radiation is in megahertz. What is the frequency of the radiation we use to get a resonance in ESR? Which range basically? Microwaves, right? So in my first class, I showed you the range even. We use frequencies of gigahertz. And when we have a frequency known, you can calculate a time scale of the resonance by taking the reciprocal of the frequencies. So the time scale is equal to 1 by mu. When we are using radio waves and when we are using microwaves, in which case is the time scale of resonance more and less? In NMR, the time scale of resonance is more because the frequency is less and there is a reciprocal relationship. Therefore, the time required for a resonance to happen is more. Whereas in ESR, the time required for the resonance to happen is less. That means what? What do you mean by more and less? In the sense, during resonance, what do you mean by resonance? It is the absorption of the electromagnetic radiation whose frequency matches the frequency of the difference in the energies between initial and final state. This is what basically resonance is. But we should also understand that while this resonance is taking place, there are other movements and motions happening in the molecule also. There are chemical and physical features keep changing in a molecule in this time scale. So when in NMR, you have a longer time for the resonance to happen because 1 by mu time scale is lesser. Longer time scale is more, frequency is less. When you have longer time to happen, resonance to happen, because of that NQR nuclear dipole moment, the nitrogen nuclei, N14 nuclei, get enough time to undergo all their possible spin states, transitions between all their spin states. Therefore, it becomes therefore, I told you why nitrogen is silent and inactive in NMR, because the nuclear quadrupole moment diminishes or quenches the interaction of the nuclear nitrogen 14 with other nuclei. But for this quenching to happen, it requires some time. And there is enough time in NMR time scale. But when it comes to ESR time scale, since we are using frequencies of radiations in microwaves and it is gigahertz. So from mega to gigahertz, almost a difference of 1000 times. So if you have to convert this into time scale, you can always tell resonance happens in ESR almost 1000 times faster compared to resonance in NMR. So because of this rapid resonance, the nuclei N14 don't get enough time to undergo all their NQR transitions and quench the interaction. Therefore, they still remain active in ESR. Okay, do you understand? So the answer lies in this time scale. Therefore, but anyways, practically, even if you don't know the theory so much behind this, it is okay that you understand this much, that hyperfine splitting, when we are doing, we have to account for the nitrogen splitting also. Fine. In fact, anyways, I'm just speaking of something which is not directly related, but somehow very relevant to this, not related, relevant to this topic of discussion. You know this uncertainty principle, right? Quantum mechanics, Heisenberg's uncertainty principle. Do you know this? So what is Heisenberg's uncertainty principle? Okay, at least the equation of that. delta x into delta p is equal to h by 2 pi. That means there are uncertainty in the position and the uncertainty in momentum. The product of that will be a constant. Now, you should also know that there are some more pairs which add up, whose combination give the same constant h. What are those some more pairs? Which one pair is position momentum pair. The other pair is energy time pair.
Time and
Yes, yes, time and energy. That pair also makes up the Heisenberg's uncertainty. Because you know what is the unit of h? Joules per sec. Joules, sorry, not joules per sec, joule sec. So any two combinations which give you the unit as joule sec should be a Heisenberg pair, basically. So this energy time pair uncertainty has a very big effect on the spectra in on different various spectra in our spectroscopies. Now, why is ESR presented as its first derivative spectrum? I mean, you see, in no other spectrum you see lines going up and down on the axis, y-axis, right? It will be only on the y-axis, tall lines or small. Maximum you can have a flat line, or minimum you can have a flat line. Only in ESR you find a spectrum like this. The lines are going up and down. Is it not? Why? Because this is a first derivative spectrum presentation. But why? Why can't it be like your NMR? How do lines look in NMR? You simply have x and y axis. They just go up. They don't come down in the negative y-axis side also. But here it happens in ESR. Actually, it is because the way we are presenting the spectrum. We present ESR in its first derivative form. So why this was required for us? Because I think in my first class I explained.
narrow.
Yes, good. Actually, the ESR spectrum lines, if you don't present as a first derivative spectrum, they are very broad. In fact, they are very broad. So when they are so broad, you cannot make a good interpretation of your spectrum. Therefore, we will refine the spectrum for our better understanding by sharpening the lines. The same broad peak, when you convert it to a differential peak by using del x by del y patterns, you get a sharp lines. Okay. So what is the point here? That the lines in the ESR are very broad if they are not presented in the first derivative pattern, first derivative mode. So why are they so broad compared to NMR? In NMR, they are not that broad, but in ESR, why are they broadened so much? The answer lies in the energy time uncertainty. Since the time of resonance is very small, very short in ESR, that is what we discussed with respect to nitrogen 14 spectrum. Very short in respect to with respect to ESR. So your del T is very small. Therefore, your del E will become large. Okay. So how to work with these Heisenberg pairs? If the uncertainty in one quantity goes down, the uncertainty in the other quantity goes up. So going back to the position momentum analogy, if you can accurately determine momentum, the uncertainty in the position is infinite. Is it not? It's basically too much. So it's like that. So a combination of these two will always be there. So since the time scale is very short, the uncertainty is very short, but the del E simultaneously, proportionally goes too much up. So if there is too much uncertainty in the delta E value, that means what? There is too much uncertainty in the frequency of the radiation absorbed. And how does this uncertainty reflect in the spectrum? By broadening of the peaks. If there was very minimum uncertainty, or in fact, ideally, if there was no uncertainty, you should have got a single line, sharp single line. Because there is uncertainty, the peak has broadened. That means what? There is no sharp frequency absorption. Rather, the frequency is absorbed in a range. A broad peak in any spectrum, what does it indicate? The absorption is not sharp. That means what? There are many closely lying frequencies which are absorbed. But anyways, we account for that whole peak as a single absorption. That is for our practical interpretation. But theoretically, it's not like that. There are many frequencies, close lying frequencies, which are getting absorbed in that range. But why does this happen? If the delta E goes up, the uncertainty in the energy goes up. Fine. So if you can increase this delta T, if uncertainty in delta T is increased, you can decrease delta E. But how to increase delta T? Then the resonance time scale should be increased. That's what happens with NMR. Resonance time scale is increased. Therefore, delta E is less. Sharp lines are obtained. Again, I mean, you can go on interconnecting your questions. Why is the time scale of resonance is so short in ESR? That is because of smaller size of electrons compared to nuclear size. Almost, the size of electron is almost negligible compared to nucleus size. Therefore, it undergoes fast transitions, very rapid resonances. That is the reason for rapid resonances in ESR compared to NMR. Anyways, so now, yes. So for N14, I is equal to, so you can have -1, 0, +1 values. With a single electron, the nitrogen nucleus splits into 3 signals. Each line is further split into 2 due to interaction with hydrogen. Therefore, you get total 6 lines. So, I mean, this is the last slide on hyperfine interactions here. We have been spending a lot of time discussing hyperfine interactions. Last slide. In fact, if you look at the actual ESR spectrum, there will be too many lines. Because, as I told you, there is not a many nuclei which are NMR silent become active in ESR. Therefore, you have an interaction, splitting happens. You have second interaction with another nucleus. There can be one more nucleus with I is equal to 1, I is equal to 3/2. So with lot of interactions, multiple levels of interactions, you get finally a spectrum like this. Can you see the final spectrum, which I labeled as C? There are too many lines. In fact, there will be many overlapping lines. Sometimes it's even difficult to count the actual number of lines correctly. For this, you require a lot of practice by looking at actual ESR spectrum to counting the lines. Certain level of training is required. Anyways, but in our syllabus, we get very simple ESR spectrum with already known lines. So don't worry about that aspect as of now. Therefore, what did I want to tell by showing this slide is, it is not as easy to interpret ESR spectrum as it is for NMR. Okay, fine. So that is the reason why ESR spectrum is complicated for interpretation. And fine. So this is our last discussion. Is there a need for reference in ESR? In NMR, how do we record a spectrum? We use an internal standard. And which is that internal standard? Which is that internal standard?
EMS.
EMS.
Yes, TMS is the internal standard. But throughout our discussion till now in ESR, we haven't even passingly mentioned anything regarding internal standard or reference. Is it not? But the technique of obtaining the spectrum is identical with NMR. So all your chemical shift values with compare with the TMS and then subtracting, dividing by field strength, it appears that we must do all those things in ESR also. Is it not? But actually there is no requirement for that in ESR. And one term which is missing in the discussion in ESR is chemical shift. In NMR, all those things we speak of is based on chemical shift values, different absorptions. But in ESR, there is no term called chemical shift. Why? Because the reference in ESR is the free electron itself. Fine. And we know the G value of a free electron accurately. That is 2.0023. Therefore, all the calibrations of the ESR instrument is done by directly taking the G value of free electron and adjusting the magnetic field and frequency to that G value of the free electron. Fine. So that is what is there in ASR. Therefore, reference is not required. G itself, G of free electron itself is a reference for us. But sometimes, particularly in solid samples, although we can put up a good argument like this, there is a G value whose value is accurately known, free electron. Still, we use a reference, and that reference is DPPH. Fine. Look at the structure of DPPH. It is 2,2-diphenyl, 1-picryl hydrazyl. You see this bond, N double bond N will be a N single bond single hydrazine, right? So I have a radical on the nitrogen. Why is this DPPH used? Because the G value of this DPPH is very closely related to G value of free electron. It is 2.0023 for free electron, whereas it is 2.0036 for DPPH. So the samples are mixed with DPPH and then their ESR is recorded. So in a way, DPPH is a TMS equivalent in ESR spectrum. Fine. Okay. So I'll just stop here. In next class, we will discuss on two other important terms called zero field splitting and Kramer's degeneracy in ESR. Fine. So if you have any doubts, please ask.